Yellowstone is rising again. That single sentence has appeared in headlines countless times over the past several decades, and almost every time it does, it triggers the same reaction. Images of a colossal supervolcano erupting begin circulating across the internet. Predictions of global catastrophe resurface. Videos claiming that the end is near attract millions of views. Yet inside the offices of the Yellowstone Volcano Observatory, the response is remarkably different. Instead of sounding alarms, scientists begin downloading fresh streams of data. They compare satellite images collected weeks apart. They examine tiny changes recorded by sensitive global positioning system stations anchored into solid bedrock. They review earthquake catalogues, gas measurements, and thermal observations, searching for patterns that might explain why a portion of Yellowstone has started moving once more. That contrast raises an intriguing question. If one of the most famous volcanic systems on Earth is lifting itself upward again, why are the people who know it best responding with careful analysis instead of panic? The answer reaches back more than a century and reveals that Yellowstone has been sending subtle signals for generations. Those signals are measured not in towering ash clouds or rivers of lava, but in movements so small they are often invisible without sophisticated instruments. Millimetre by millimetre, inch by inch, the landscape changes. Sometimes it rises. Sometimes it sinks. Sometimes it does both within the span of only a few years. Understanding why has become one of the greatest scientific challenges in modern volcanology. Stretching across northwestern Wyoming and extending into parts of Montana and Idaho, Yellowstone National Park covers roughly 3,472 square miles, or nearly 8,991 square kilometers. Millions of visitors arrive each year to admire Old Faithful, the brilliantly coloured hot springs, steaming fumaroles, bubbling mud pots, and dramatic canyons. To most, it appears to be an extraordinary wilderness shaped by ancient volcanic forces long ago. Scientists see something very different. They see an immense volcanic system that is still alive. Yellowstone is not a conventional volcano with a steep cone rising above the landscape. It is a caldera, an enormous volcanic depression formed after colossal eruptions emptied vast magma reservoirs and caused the overlying crust to collapse. The present caldera, measuring approximately 30 miles by 45 miles, or about 48 by 72 kilometers, was created around 631,000 years ago during the Lava Creek eruption, the most recent of Yellowstone's 3 giant caldera-forming events. Those eruptions transformed the landscape of western North America. The oldest, known as the Huckleberry Ridge eruption, roughly 2,100,000 years ago, expelled an extraordinary volume of volcanic material across much of the continent. The Mesa Falls eruption followed approximately 1,300,000 years ago. Then came the Lava Creek eruption, whose ash eventually settled across large portions of what is now the United States. Although no eruption on that scale has occurred since, Yellowstone has never become geologically inactive. Smaller lava flows continued for tens of thousands of years after the last supereruption. Thousands of hydrothermal features remain active today. Earthquakes occur every year. Heat continues rising from deep within the crust. All of these observations indicate that the magmatic system responsible for Yellowstone still exists. For much of the 20th century, however, scientists assumed that the caldera itself remained relatively stable. Without continuous satellite observations or dense monitoring networks, there was little reason to suspect that the entire landscape might be slowly moving. That assumption began to unravel through the meticulous work of surveyors. Long before satellites orbited Earth, engineers relied on precision leveling surveys to detect changes in elevation. Using carefully calibrated optical instruments, they established reference benchmarks across the landscape and repeatedly measured differences in height over many years. The process demanded extraordinary patience. Even small measurement errors had to be eliminated because the changes being sought were often only fractions of an inch or a few millimeters. As additional surveys accumulated through the decades, a surprising pattern began to emerge. The land inside Yellowstone's caldera was no longer occupying exactly the same position it had decades earlier. One of the landmark discoveries arrived in the late 1970s. In a paper published in Science during 1979, geophysicists J.R. Pelton and Robert B. Smith compared historical leveling surveys conducted during the 1920s with modern surveys completed during the 1970s. Their analysis produced results that immediately captured the attention of volcanologists around the world. Rather than finding a stable volcanic landscape, they documented widespread uplift centered within the Yellowstone caldera. In some locations, the surface had risen by more than 2 feet or over 70 centimeters since the earlier surveys. Averaged across the observation period, parts of the caldera were rising at roughly 1/2 inch per year, or about 14 millimeters annually. For a volcanic system believed to be relatively quiet, those numbers were astonishing. Landscapes do not lift themselves upward without a source of energy. Pelton and Smith proposed that the most likely explanation involved magma, or partially molten rock, slowly intruding into the shallow crust beneath Yellowstone. As additional molten material accumulated at depth, pressure increased, gently arching the overlying surface upward. The process resembled inflating an enormous cushion buried several miles underground. No explosions, no lava fountains, no dramatic warning visible to tourists. Just an immense section of Earth's crust quietly changing shape over time. Their work marked a turning point in Yellowstone research. Instead of viewing the caldera as a dormant remnant of prehistoric eruptions, scientists increasingly recognized it as a dynamic volcanic system capable of changing even during periods without eruptions. The discovery also raised questions that proved far more difficult than the measurements themselves. If magma was moving beneath Yellowstone, why had no eruption followed? Elsewhere in the world, volcanic inflation often precedes eruptive activity. At volcanoes such as Mount St. Helens, Kilauea or Etna, swelling ground can indicate magma is approaching the surface. Yet Yellowstone refused to follow such straightforward rules. Years passed, then decades. Despite measurable uplift, no eruption occurred. Instead, something even more puzzling happened. The upward movement slowed. In some places, it stopped altogether. Then, over time, parts of the caldera actually began sinking. This unexpected reversal challenged the simplest explanations. If magma alone were responsible, why would the surface alternate between rising and falling? Scientists realized they were observing something far more complicated than a steadily filling magma chamber. Yellowstone appeared to behave more like a living system responding to changing pressures deep within the crust. By the closing years of the 20th century, technology was advancing rapidly. Instruments capable of measuring movement within mere fractions of an inch or just a few millimeters were becoming increasingly available. The era of occasional surveying was coming to an end. A new generation of continuous monitoring was about to reveal that Yellowstone's subtle movements were far more complex than anyone had imagined. Even as visitors watched Old Faithful faithfully launch columns of steaming water into the Wyoming sky, another revolution was quietly unfolding. Scientists were preparing to replace scattered measurements collected years apart with a network capable of watching Yellowstone every hour of every day. They would soon discover that the caldera was not simply rising or sinking. It was doing both, sometimes over remarkably short periods, revealing a restless volcanic system whose behavior would reshape decades of scientific thinking. The realization that Yellowstone could rise was remarkable enough. The discovery that it could also sink, then rise again, proved even more surprising. Instead of behaving like a volcano, slowly filling with magma until it erupted, Yellowstone appeared to follow a far more complicated rhythm. Every new survey hinted that the forces operating several miles below the surface were constantly changing. Pressure built, pressure eased, and the landscape responded accordingly. Scientists had uncovered a mystery, but the tools available during the late 20th century were still too limited to explain it. That began to change as the Global Positioning System, better known as GPS, transformed Earth science. Originally developed for navigation, GPS quickly became one of the most powerful tools ever applied to volcanology. By installing permanent receivers anchored directly into solid bedrock, researchers could determine the exact position of a point on Earth's surface with astonishing precision. Repeated measurements were no longer separated by years or decades. Instead, they arrived every day, allowing scientists to watch Yellowstone move almost in real time. The improvements did not stop there. Another breakthrough arrived from hundreds of miles or several hundred kilometers above the planet. Satellites carrying radar instruments introduced a technique known as interferometric synthetic aperture radar, or INSAR. Rather than relying on photographs, these satellites transmitted microwave radar pulses toward Earth's surface. By comparing the returning signals collected during repeated satellite passes, scientists could calculate changes in elevation with an accuracy measured in mere millimeters. Entire volcanic fields could now be mapped repeatedly without anyone setting foot inside the caldera. For Yellowstone, this represented a revolution. Instead of depending on scattered benchmarks connected by painstaking leveling surveys, researchers could observe deformation across nearly the entire volcanic system. Every subtle rise and every slight depression became visible. The volcano was no longer being sampled at isolated points. It was being watched as a complete living system. As the amount of data increased through the late 1980s and 1990s, one conclusion became impossible to ignore. Yellowstone did not rise continuously. Periods of inflation were repeatedly followed by subsidence. The surface behaved almost like a slowly expanding and contracting structure responding to changing pressure deep underground. Yet the pattern was irregular. Some areas rose while others remained stable. Certain regions subsided even as neighboring sections continued lifting. Whatever mechanism controlled Yellowstone was clearly more complex than a single underground chamber filling with molten rock. To understand these changing movements, scientists expanded the monitoring network across Yellowstone and the surrounding Snake River Plain. Dozens of GPS stations began collecting uninterrupted observations. Seismometers recorded thousands of earthquakes each year. Gravity surveys searched for changes in underground mass. Geologists mapped fractures and faults, Every new data set became another piece of a puzzle that refused to reveal its full picture. One of the most comprehensive analyses emerged in 2007, when Esther Puskas and colleagues published their research in the Journal of Geophysical Research. Drawing upon GPS observations collected between 1987 and 2004, the team assembled one of the clearest records yet of Yellowstone's long-term deformation. Their findings overturned a common public misconception. Many people imagined Yellowstone as a supervolcano steadily building toward a future eruption, its surface rising higher each year as magma accumulated below. The GPS data told a very different story. The caldera experienced repeated cycles: inflation, deflation, renewed inflation, renewed subsidence. Maximum deformation rates reached approximately 3/5 of an inch each year, or about 15 millimeters annually, but those rates varied over time and across different parts of the volcanic system. Yellowstone behaved less like a balloon being continuously inflated and more like an enormous pressure vessel whose internal forces were constantly adjusting. The researchers concluded that these changes reflected variations in pressure within Yellowstone's interconnected magma and hydrothermal system. That distinction was crucial. For decades, magma had been viewed as the primary explanation for volcanic deformation. The new GPS observations suggested another major player was involved: water. Not ordinary groundwater, but vast quantities of superheated water circulating through fractured volcanic rock. Yellowstone contains the largest concentration of hydrothermal features on Earth. More than 10,000 geysers, hot springs, fumaroles and mud pots release heat generated by the underlying magmatic system. Rainfall and melting snow slowly seep downward through networks of cracks before encountering intensely heated rock. The water becomes superheated under immense pressure, dissolving minerals and gases as it circulates through the crust. Because it remains trapped beneath the surface, the water does not immediately boil, even though its temperature exceeds the normal boiling point. Instead, pressure allows it to store enormous amounts of thermal energy. As that pressure changes, the surrounding rock can expand or contract slightly, producing measurable deformation at the surface. This realization fundamentally changed scientific thinking. Yellowstone's uplift was no longer interpreted solely as magma forcing its way upward. Hydrothermal fluids could also produce significant ground movement. In some situations, both processes might occur simultaneously. Distinguishing between them became one of the greatest challenges facing volcanologists. A few centimeters, or about 1 inch, of uplift could indicate fresh magma entering the crust. The same amount of uplift might instead result from changes in underground water pressure. From the surface alone, the two possibilities could appear remarkably similar. Scientists therefore began combining multiple lines of evidence before drawing conclusions. GPS measurements were compared with earthquake activity. Gas emissions were analysed for changes in carbon dioxide and sulfur dioxide. Heat flow was monitored across geothermal areas. Satellite imagery tracked temperature variations. Every observation had to fit together before researchers could confidently interpret what Yellowstone was doing. This multidisciplinary approach reflected an important lesson learned from volcanoes around the world. No single warning sign is reliable by itself. A volcano may inflate without erupting. Earthquake swarms may occur without magma approaching the surface. Gas emissions may fluctuate because of changes in underground plumbing rather than fresh magma intrusion. Only when several independent indicators change together does concern begin to increase. Yellowstone repeatedly demonstrated this principle. Throughout the 1990s, periods of uplift occurred without corresponding increases in volcanic unrest. Earthquake activity remained within expected ranges. Gas measurements showed no dramatic shifts. Hydrothermal areas continued behaving much as they had for decades. Although the landscape moved, the broader volcanic system remained remarkably stable. Even so, researchers understood that they were observing one of the most unusual volcanic complexes on Earth. Unlike steep stratovolcanoes, where magma often follows relatively narrow conduits toward the surface, Yellowstone's magmatic system extends across a vast area. Heat, fluids, faults, and partially molten rock interact within a crust that has been repeatedly fractured by millions of years of volcanic activity. Every new measurement hinted at that complexity. Pressure generated in one location could influence another several miles or several kilometers away. Hydrothermal reservoirs might respond to subtle changes in stress. Faults could open or close, redirecting fluid pathways through the crust. The volcano was not governed by a single chamber or a single process. It resembled an intricate network whose components constantly influence one another. Yet the most dramatic discovery was still ahead. Despite decades of careful monitoring, scientists had never witnessed Yellowstone changing elevation at truly extraordinary rates. The historical uplift documented by Pelton and Robert B. Smith had unfolded over many years. The GPS observations revealed repeating cycles, but none suggested rapid acceleration. That changed early in the 21st century. As satellites continued passing overhead and GPS receivers transmitted uninterrupted streams of data, researchers noticed something that immediately captured their attention. Parts of Yellowstone were no longer rising gradually over decades. They were rising at speeds unlike anything previously recorded within the modern monitoring era. The discovery would lead to one of the most influential Yellowstone studies ever published, uniting satellite radar, GPS observations and field measurements into compelling evidence that deep within the volcanic system, powerful forces had once again begun reshaping the caldera. The new century brought with it a level of precision that earlier generations of volcanologists could scarcely imagine. Every passing satellite added another layer of information. Permanent GPS stations transmitted measurements day after day without interruption. Seismometers listened continuously for even the faintest earthquakes. Yellowstone was no longer being observed only during scientific expeditions. It had become one of the most heavily instrumented volcanic systems on Earth, generating an enormous stream of data that allowed researchers to detect changes almost as soon as they occurred. Then the numbers began to change. Between the years 2004 and 2006, several GPS stations inside Yellowstone caldera recorded a pattern that immediately stood out from previous decades. The surface was rising again, but this time the rate of uplift appeared unusually rapid. Independent measurements from satellite radar confirmed the same trend. Multiple instruments using entirely different methods were arriving at the same conclusion. The caldera was inflating faster than anyone had expected. Those observations became the focus of one of the most influential Yellowstone studies ever published. In 2006, Charles Wicks, Wayne Thatcher, Daniel Zurisin, and Jerry Svark presented their findings in the journal Nature. Rather than relying on a single monitoring technique, the team combined continuous GPS observations, interferometric synthetic aperture radar, traditional ground surveys and deformation modelling to reconstruct what had been happening beneath Yellowstone during the previous several years. The results immediately attracted international attention. Some locations inside the caldera had risen by nearly 3 inches, or about 7 centimeters, within only 3 years. At certain GPS stations, the annual rate of uplift approached almost 3 inches each year, or roughly 7 centimeters annually. Compared with previous observations, these were among the fastest deformation rates ever documented at Yellowstone since modern geodetic monitoring began. To the public, those figures sounded alarming. To volcanologists, they represented something equally compelling: evidence. Unlike rumours or speculation, deformation could be measured with extraordinary precision. GPS receivers anchored into bedrock had no opinions. Radar satellites did not exaggerate. Every independent data set pointed toward the same conclusion. Something beneath Yellowstone was increasing pressure within the crust. The next question proved far more difficult. What exactly was creating that pressure? Using mathematical deformation models, the researchers estimated that the source responsible for the uplift was located approximately 6 miles, or about 10 kilometers, below the surface. That depth corresponded to the upper portions of Yellowstone's magmatic system, where earlier geophysical studies had already suggested the presence of partially molten rock. One explanation appeared straightforward. Fresh magma was slowly entering an existing underground reservoir. As new molten material accumulated, pressure increased. The overlying crust responded elastically, arching upward much like the surface of a gently inflating dome. This mechanism had been observed at volcanoes around the world and was entirely consistent with established principles of rock mechanics. Yet Yellowstone rarely offers simple answers. The deformation models produced another important conclusion. Magma alone could not fully explain every observation. The researchers proposed that hydrothermal fluids were likely contributing to the deformation as well. Heated groundwater circulating through Yellowstone's fractured volcanic rocks could alter underground pressure, redistribute stress, and influence surface movement. Instead of one driving force, the caldera appeared to be responding to the combined effects of magmatic intrusion and an extraordinarily active hydrothermal system. That distinction was critical. Yellowstone contains one of the most extensive hydrothermal systems on the planet. Heat escaping from the underlying magma continuously warms groundwater that penetrates deep into fractured volcanic rock. As the water becomes superheated, it expands, dissolves minerals, transports gases, and migrates through complex networks of faults and fractures. These fluids are anything but passive. Changing pressure within hydrothermal reservoirs can deform the surface, trigger earthquake swarms, alter geyser behavior, and even produce violent hydrothermal explosions without requiring fresh magma to approach the surface. For Yellowstone, this meant that uplift no longer had a single interpretation. The same movement measured by GPS could result from increasing magma pressure. It could also result from changing hydrothermal pressure, or both processes could be operating simultaneously. Distinguishing between those possibilities required far more than measuring elevation. Researchers began integrating multiple data sets into a single framework. Seismic activity was compared with deformation patterns. Gas emissions were analyzed for changes in carbon dioxide, sulfur dioxide, and hydrogen sulfide. Thermal imagery searched for new areas of increased heat flow. Gravity measurements helped estimate whether underground mass distributions were changing. Every dataset served as another clue pointing toward the underlying processes. The approach reflected a broader transformation taking place across volcanology. Earlier generations often relied upon isolated observations. Modern volcano science depended upon integration. No instrument alone could reveal the complete picture. GPS might detect uplift. Seismometers could identify migrating earthquake swarms. Gas sensors measured volcanic emissions. Satellite radar mapped deformation across entire volcanic fields. Geochemical sampling monitored changes in hot spring chemistry. Only by combining all these observations could scientists begin separating ordinary volcanic behavior from signs of escalating unrest. Yellowstone quickly became one of the world's greatest natural laboratories for testing that approach. The 2006 Nature paper also highlighted an important lesson for hazard communication. Rapid uplift, impressive as it appeared, was not accompanied by other indicators that would normally suggest an eruption was becoming imminent. Earthquake activity fluctuated within expected ranges. Gas emissions showed no dramatic changes, pointing toward rapidly ascending magma. Hydrothermal systems remained active, but largely within historical behavior. In other words, Yellowstone was changing. But it was not behaving like a volcano preparing to erupt. This conclusion frustrated those hoping for simple answers. Many people wanted a single measurement that could predict the next eruption. Scientists increasingly recognized that such a measurement probably does not exist. Volcanoes operate through interconnected physical systems that evolve over time. Pressure can increase without producing an eruption. Magma can intrude and later cool. Fluids can migrate through fractures, redistributing stress across broad regions. Faults can slip, relieving pressure that had accumulated over months or years. Yellowstone demonstrated all of these possibilities. As researchers continued analyzing the deformation, another realization gradually emerged. The volcanic system was not merely responding to magma entering from below. Its internal plumbing appeared astonishingly intricate. Heat generated by magma interacted continuously with groundwater. Faults created pathways for fluids to migrate. Mineral deposits gradually sealed some fractures, while earthquakes opened others. Pressure changes occurring miles or kilometers underground could eventually influence the behavior of geysers at the surface. Understanding Yellowstone therefore required more than mapping a magma chamber. Scientists needed to understand an entire subterranean ecosystem. Advances in seismic imaging soon began revealing that hidden world in remarkable detail. By studying the speed at which earthquake waves traveled through the crust, geophysicists could construct three-dimensional images of rock layers buried several miles or several kilometers below the surface. Those images would overturn another widespread misconception about Yellowstone. Contrary to popular imagination, researchers did not find an immense underground ocean of liquid lava waiting to erupt. They discovered something far more complex, an enormous crystalline reservoir containing only a modest fraction of molten rock, intertwined with heat, gases, and hydrothermal fluids. That revelation would fundamentally change how scientists understood Yellowstone's ability to rise, fall, and remain active without producing the catastrophic eruption so often imagined by the public. The image most people carry in their minds is remarkably simple. Somewhere beneath Yellowstone, they imagine a gigantic chamber filled with glowing liquid lava, waiting for enough pressure to burst through the surface. It is an image reinforced by movies, television specials, and countless internet illustrations. It is also one of the biggest misconceptions ever associated with the Yellowstone volcanic system. Modern geophysics has revealed something far more fascinating. Scientists cannot drill several miles or several kilometers into Yellowstone to look directly at its magma reservoirs. Temperatures exceed anything conventional drilling equipment can withstand, and the depths involved make such an effort impractical. Instead, researchers rely on methods similar to a medical computed tomography scan. Rather than using X-rays, they use earthquake waves generated by natural earthquakes occurring throughout the western United States. Every earthquake sends seismic waves through Earth's interior. Those waves travel at different speeds, depending on the material they encounter. Solid, cold rock allows seismic energy to move relatively quickly. Hot rock slows it down. Partially molten rock slows it even more. By recording these travel times at hundreds of seismic stations, scientists can reconstruct three-dimensional images of the crust and upper mantle hidden beneath Yellowstone. One of the leading figures behind this work has been Robert B. Smith of the University of Utah, whose decades of research transform modern understanding of the Yellowstone hotspot. Together with numerous collaborators, Smith combined seismic observations, geologic mapping, geodesy, and earthquake data to reveal a volcanic system vastly more complicated than scientists had imagined during the 20th century. As computing power improved, the images became increasingly detailed. Then, during the 21st century, another major breakthrough arrived. Using seismic tomography, Xinhua Huang and colleagues published research revealing that Yellowstone's magmatic system consists of multiple interconnected reservoirs rather than one enormous pool of molten rock. Their work, together with earlier imaging studies led by Jamie Farrell, showed that a shallower magma reservoir lies approximately 3 to 10 miles, or about 5 to 16 kilometers, below the surface. Far deeper, extending into the upper mantle, exists a much larger reservoir of hot material feeding heat toward the crust. At first glance, those discoveries seem to confirm the public's fears. Multiple magma reservoirs, heat rising continuously from Earth's interior, one of the largest volcanic systems on the planet. Yet the most important finding was not their size. It was their composition. Contrary to countless illustrations portraying an underground sea of liquid lava, the shallow reservoir contains far more solid rock than molten material. Researchers estimate that only about 5 to 15% of the upper reservoir is actually molten at any given time. The remaining volume consists largely of hot, crystalline rock. Individual pockets of melt occupy spaces between mineral crystals, producing what volcanologists often describe as a crystal mush. The term may sound unremarkable, but it fundamentally changes the way Yellowstone operates. Imagine a sponge soaked with water. The sponge itself represents the crystalline framework of the reservoir. The water filling the spaces between the fibers represents molten rock. Although liquid is present, it does not flow freely like water inside a bucket. Movement depends on temperature, pressure, and the connections between those melt-rich zones. Yellowstone behaves in much the same way. Its magma reservoir is not an underground lake waiting to burst open. Instead, it resembles a vast framework of crystals containing interconnected pockets of molten rock, dissolved gases, and superheated fluids. This structure is capable of storing enormous amounts of heat for hundreds of thousands of years without necessarily producing an eruption. That realization solved one mystery while creating another. If only a relatively small percentage of the reservoir is molten, why does the surface continue rising and falling? The answer lies in the remarkable relationship between heat, fluids, and pressure. As magma slowly transfers heat into the surrounding crust, groundwater circulating through fractures becomes superheated. Minerals dissolve. Volcanic gases, such as carbon dioxide, accumulate within the fluid. Pressure builds inside networks of cracks extending through the volcanic rocks. Unlike rigid concrete, Earth's crust behaves elastically over geological timescales. Increase pressure deep underground, and the overlying rocks flex upward. Reduce that pressure, and the rocks gradually settle again. The amount of movement measured at the surface may be only fractions of an inch, or a few millimeters, or a few inches, or several centimeters, yet those subtle changes reflect enormous volumes of rock responding to forces operating several miles or several kilometers below. Scientists describe this interaction as a coupled magmatic hydrothermal system. The phrase reflects one of the most important concepts in Yellowstone research. The magma reservoir cannot be studied in isolation. Neither can the hydrothermal system. Each influences the other continuously. Fresh magma entering the reservoir increases heat. Additional heat changes groundwater circulation. Changing groundwater pressure alters stress within surrounding rocks. Stress influences fault movement. Fault movement changes pathways for fluid circulation. Those new pathways may alter geyser behavior, trigger earthquake swarms, or redistribute pressure across different parts of the caldera. Every component is connected. This interconnected behavior helps explain why Yellowstone often appears unpredictable. 1 year, GPS stations may record uplift. A few years later, subsidence begins. Earthquake swarms migrate from one region to another. A geyser dormant for decades suddenly becomes active. Elsewhere, long-established thermal pools cool unexpectedly. None of these observations necessarily indicates that magma is racing toward the surface. Instead, they demonstrate that Yellowstone functions as an extraordinarily dynamic geological system in which small adjustments deep underground can produce measurable changes across a vast area. One striking example involves Steamboat Geyser, located within Norris Geyser Basin. For many years, Steamboat erupted only sporadically, with unpredictable intervals separating major eruptions. Then, beginning in 2018, its behavior changed dramatically. The geyser entered one of the most active periods ever documented, producing frequent water eruptions that drew worldwide attention. Scientists immediately began asking whether the renewed activity reflected deeper volcanic changes. After extensive analysis, researchers concluded that the answer was probably more complicated. While Steamboat's activity likely reflected changes within the hydrothermal plumbing system, there was no compelling evidence linking the eruptions to fresh magma rapidly approaching the surface. Variations in groundwater supply, underground permeability, pressure redistribution, and seasonal conditions all appeared capable of influencing geyser behavior. Once again, Yellowstone resisted simple explanations. The same lesson applied repeatedly throughout the caldera. A change observed at the surface could originate from processes occurring only a few hundred feet or several dozen meters underground, or several thousand feet, or around 1 kilometer, or several miles, or several kilometers. Determining which explanation was correct required integrating every available source of information. By now, scientists had developed an increasingly detailed picture of Yellowstone's hidden interior. They understood that the crust contained crystal-rich magma reservoirs rather than vast liquid lakes. They recognized that hydrothermal fluids played a central role in deformation. They had documented repeated cycles of uplift and subsidence spanning decades. Yet one crucial question remained unresolved. If the hydrothermal system was capable of reshaping Yellowstone's surface without requiring an eruption, just how powerful could that system become? The answer was preserved in the landscape itself, hidden in giant craters, ancient explosion deposits, and steaming basins that revealed a surprising truth. At Yellowstone, some of the most violent geological events do not involve lava at all. Visitors standing beside Yellowstone's colourful hot springs often focus on their extraordinary beauty. Brilliant shades of blue, green, orange and gold stretch across pools of steaming water. Towering geysers launch columns of boiling water hundreds of feet or tens of meters into the air. Thick clouds of steam drift across the landscape, carrying the unmistakable scent of sulfur. It is one of the most spectacular geothermal landscapes anywhere on Earth. Yet these remarkable features are far more than tourist attractions. They are windows into one of the largest hydrothermal systems on the planet. Yellowstone contains more than 10,000 hydrothermal features, representing over half of all known geysers worldwide. No other place possesses such an extraordinary concentration of geothermal activity. Every hot spring, mud pot, fumarole and geyser exists because enormous quantities of heat continue rising from the magmatic system buried several miles or several kilometers below the surface. That heat drives an endless cycle. Snow and rain falling across Yellowstone slowly infiltrate the fractured volcanic rocks. Over months, years, and sometimes decades, the water descends deeper into the crust through networks of cracks and faults. As it approaches increasingly hotter rocks, its temperature rises dramatically. Under the immense pressure of the overlying rock, the water remains liquid despite reaching temperatures well above the normal boiling point. Eventually, the superheated water begins moving upward again. Along the way, it dissolves silica, sulfur compounds, carbon dioxide, and numerous other minerals. Some of these minerals later precipitate near the surface, building the spectacular terraces of Mammoth Hot Springs or the silicious deposits surrounding famous geysers like Old Faithful. The process appears gentle from above. Deep underground, however, it involves tremendous energy. 1 gallon, or approximately 3.8 litres of water expanding into steam, can increase its volume by roughly 1,700 times under the right conditions. When that transformation occurs within confined fractures beneath the surface, pressures rise with astonishing speed. If surrounding rocks can no longer contain that pressure, they may fracture violently. Unlike a volcanic eruption driven by ascending magma, these events are powered primarily by water. Scientists refer to them as hydrothermal explosions. Among the researchers who has spent years explaining these hazards is Michael Poland, scientist in charge of the Yellowstone Volcano Observatory. Through numerous United States Geological Survey publications and public briefings, Poland has repeatedly emphasized that hydrothermal explosions represent one of the more realistic geological hazards visitors could encounter inside Yellowstone National Park. That statement surprises many people. Public attention almost always focuses on the possibility of another super-eruption. Scientists, however, understand that hydrothermal explosions have occurred repeatedly throughout Yellowstone's history and will almost certainly occur again long before another caldera forming eruption. Some hydrothermal explosions are relatively small, scattering rocks only a short distance. Others have been enormous. One of the most dramatic examples lies along the northern shore of Yellowstone Lake. Known as Mary Bay, The broad circular depression is not an impact crater and not the product of lava erupting from a volcanic vent. Geological investigations indicate that it formed approximately 13,000 years ago, when superheated groundwater flashed almost instantaneously into steam. The resulting explosion excavated a crater more than 1 mile across, or roughly 2.5 kilometers in diameter, blasting enormous quantities of rock and sediment across the surrounding landscape. The force required to create such a crater is difficult to comprehend. Yet no fresh magma needed to reach the surface. The explosion occurred because water stored immense thermal energy while confined beneath layers of rock. Once that pressure was released, the rapid expansion of steam transformed underground heat into explosive mechanical force. Mary Bay is not unique. Geologists have identified numerous explosion craters scattered throughout Yellowstone National Park. Some are hidden beneath forests, others have filled with lakes over thousands of years. Together they reveal that hydrothermal explosions have been recurring features of Yellowstone's geological evolution since the last major volcanic eruptions. Most receive little public attention, yet they provide critical insight into the volcano's hidden plumbing system. Unlike magma, which may remain deep underground for centuries without moving significantly, hydrothermal fluids circulate continuously. They migrate through fractures, dissolve minerals, deposit new material, seal existing pathways, and occasionally create entirely new ones. Every earthquake, every pressure change, and every subtle shift in crustal stress can alter that circulation. This explains why Yellowstone sometimes surprises scientists with unexpected changes. A hot spring that has flowed steadily for decades may suddenly become cloudy. A fumarole may increase its steam output. A dormant vent may begin emitting gas. Elsewhere, a thermal pool may cool as underground water is diverted into newly opened fractures. These changes do not necessarily indicate fresh magma intrusion. Often they reflect adjustments occurring within the hydrothermal plumbing itself. One of the clearest demonstrations occurred following the magnitude 7 3/10 Hebgen Lake earthquake in 1959, just northwest of Yellowstone National Park. Although the earthquake did not originate beneath the caldera, the powerful shaking altered numerous hydrothermal features throughout Yellowstone. Some geysers erupted more frequently, others became temporarily inactive. Water levels changed. New springs appeared while older ones diminished. The earthquake had effectively rearranged portions of Yellowstone's underground plumbing. Scientists realized that the hydrothermal system was extraordinarily sensitive to even modest changes in crustal stress. That sensitivity also helps explain why Yellowstone's surface sometimes rises without signaling an impending eruption. As fluids accumulate within underground reservoirs, pressure increases. The surrounding rocks respond elastically. GPS stations record uplift. Later, fluids migrate into neighboring fractures or escape through geothermal features. Pressure decreases. The surface subsides once again. No eruption is required. No fresh magma must necessarily enter the system. Instead, Yellowstone is continually adjusting to the movement of heat and fluids through one of the most complex geothermal environments ever studied. This understanding became increasingly important as monitoring technology improved. Whenever GPS instruments detected renewed uplift, researchers no longer assumed magma was solely responsible. Instead, they asked a series of increasingly sophisticated questions. Were earthquake swarms occurring simultaneously? Had gas emissions changed? Was heat flow increasing? Were hydrothermal features behaving unusually? Did satellite radar reveal localized deformation, or widespread inflation? Each answer narrowed the range of possible explanations. Over time, scientists developed a far more nuanced picture of Yellowstone's behavior. Rather than viewing the volcano as alternating between quiet and active, they recognized that Yellowstone exists in a state of continuous unrest. The phrase does not imply imminent danger. Instead, it reflects the reality that Yellowstone is almost always changing. Steam rises every day. Earthquakes occur every week. Geysers erupt every hour. Heat escapes continuously. The crust expands and contracts over periods ranging from days to decades. Restlessness is the normal condition of the Yellowstone volcanic system. This realization dramatically changed the philosophy of volcanic monitoring. Scientists were no longer searching for activity. Activity was constant. The challenge became identifying the rare signals that truly differed from Yellowstone's ordinary behavior. Doing so required understanding another phenomenon that has puzzled researchers for decades. Almost every year, sometimes for weeks at a time, Yellowstone begins trembling with hundreds of earthquakes clustered within remarkably small areas. These events often occur without causing damage, yet they reveal another critical process operating deep inside the volcanic system. They are known as earthquake swarms, and no volcanic region in North America experiences them quite like Yellowstone. Earthquake swarms are common at Yellowstone. Researchers therefore pay close attention to the depth, location, and migration of seismic events. If earthquakes begin moving steadily upward through the crust over time, forming patterns consistent with magma ascending toward the surface, concern would increase considerably. Such migrating earthquake sequences have been documented before eruptions at volcanoes around the world because brittle rocks fracture as magma forces its way upward. Yellowstone has not displayed such behavior. Instead, most earthquake swarms remain confined to known fault systems or regions dominated by hydrothermal circulation. The second signal involves volcanic gases. As magma rises, pressure decreases. That reduction in pressure allows dissolved gases to escape from the molten rock, much like bubbles escaping when a bottle of carbonated water is opened. Scientists therefore monitor gases such as carbon dioxide, sulfur dioxide, and hydrogen sulfide throughout Yellowstone. Carbon dioxide is particularly important because it can escape from magma at greater depths than many other volcanic gases. An abrupt, sustained increase in emissions across multiple monitoring sites could indicate that fresh magma is moving upward. So far, Yellowstone's gas measurements have remained broadly consistent with long-term observations, fluctuating naturally without suggesting major changes in the magmatic system. Heat provides another critical clue. The Yellowstone Plateau already releases an enormous amount of geothermal energy every day. Heat continuously escapes through thousands of geysers, hot springs, steam vents, and warm ground. Researchers carefully measure this heat using field instruments, aircraft surveys, and thermal imaging satellites. A significant, widespread increase in heat flow would attract immediate scientific attention. It could suggest that additional magma was transferring more energy into the hydrothermal system. To date, no such park-wide thermal increase has accompanied recent uplift episodes. Scientists would also examine Yellowstone's hydrothermal features. The park's geysers and hot springs respond naturally to seasonal changes, precipitation, earthquakes, and subtle variations in underground pressure. Individual features frequently change behavior. That alone is not unusual. However, simultaneous changes affecting numerous geothermal basins across the entire caldera would represent something quite different. Researchers would carefully compare those observations with deformation, seismicity, gas emissions, and heat flow before drawing conclusions. Perhaps the most revealing indicator would involve the combination of all these signals occurring together. Imagine GPS stations recording rapid, accelerating uplift across much of the caldera. At the same time, earthquake swarms begin migrating upward through the crust. Gas emissions increase substantially. Heat flow rises across multiple geothermal basins. New fractures appear at the surface. Hydrothermal systems undergo widespread coordinated changes. Taken individually, each observation might have several possible explanations. Taken together, they would present a far more compelling case that the volcanic system was entering an unusual state. This principle has guided volcanic monitoring worldwide for decades. One volcano illustrates the point particularly well. Before the eruption of Mount St. Helens in 1980, scientists observed a remarkable sequence of reinforcing signals. Earthquake activity intensified dramatically. A conspicuous bulge developed on the volcano's northern flank as magma intruded into the mountain. Steam explosions occurred repeatedly. Gas emissions changed. The deformation accelerated over time. No single observation proved an eruption was inevitable. Together, however, they painted an unmistakable picture of escalating volcanic unrest. Yellowstone has never exhibited that complete suite of warning signs during the modern monitoring era. Another useful comparison comes from Kilauea in Hawaii. Before many of its eruptions, researchers have documented coordinated changes involving earthquake migration, summit inflation, volcanic gas emissions, and magma movement detected through deformation measurements. Again, the power of volcanic forecasting lies not in any individual signal, but in their combined evolution. This is precisely why the Yellowstone Volcano Observatory employs specialists from multiple scientific disciplines. Seismologists analyze earthquakes, geodesists measure deformation, geochemists monitor volcanic gases, hydrologists study groundwater, geophysicists construct models of magma movement, remote sensing specialists interpret satellite observations. No single expert possesses all the answers. Instead, understanding Yellowstone requires integrating evidence from every available source. That collaborative approach has repeatedly demonstrated its value. When the Norris uplift began around July of 2025, scientists did not rely solely on GPS measurements. They examined seismic records. They reviewed satellite radar data. They analyzed geothermal observations. They compared the new deformation with Yellowstone's extensive historical record. The conclusion reflected decades of accumulated knowledge. The uplift represented another localized inflation event within Yellowstone's dynamic magmatic hydrothermal system. It did not indicate that an eruption was imminent. That careful distinction is perhaps the most important message scientists have communicated over the past 50 years. Yellowstone deserves close attention because it remains an active volcanic system. It does not deserve exaggerated claims unsupported by evidence. Its history demonstrates both extraordinary power and remarkable patience. The caldera has spent generations rising and falling, releasing pressure, redistributing fluids, and reshaping itself without progressing toward a major eruption. Every new episode of Uplift adds another chapter to that history rather than rewriting it. Yet scientists continue watching with unwavering attention. Not because they expect catastrophe tomorrow, but because Yellowstone has shown that even the smallest movement, A few millimeters measured by a GPS antenna, a subtle shift detected by a passing radar satellite, or a cluster of tiny earthquakes deep within the crust can reveal something profound about the hidden processes operating inside one of Earth's most extraordinary volcanic systems. The next chapter in Yellowstone's history will almost certainly begin the same way the previous ones did. Not with a towering column of ash, but with an instrument quietly recording that the landscape has started to move once again.